What?
What's wrong, Markku?
Well, Michael, I don't understand how this is happening. Why is my skinny pencil, upon being submerged in water, appearing fatter? And more importantly, how is it changing direction? This is mind-boggling. Could you somehow explain this to me?
Sure, no problem, Markku. You see, what you are witnessing is a phenomenon known as refraction, and it was first observed by Thomas Harriot of England way back in 1602. But he died before he could publish his findings, and he was ripped off by Willebrord van Rooyen Snell, who attempted to publish Harriot's notes, but he also died before he succeeded. Finally, René Descartes published them in 1637, almost 40 years after Harriot's death.
I don't really care. I want to know why my straw is morphing into a bigger size and changing direction. I don't need a history lesson.
Well, Markku, light that enters or exits water is actually bent by refraction. The index of refraction for water is 4/3, which means that light itself travels 3/4 as fast in water as it does in a vacuum.
That would be a great explanation if I knew what an index of a refraction was.
Let me explain. The index of refraction is the speed of the light in a vacuum divided by the speed of the light in the medium.
What's a medium?
The medium is what the light is actually going into or passing through. It's the substance or the surface that the light hits.
I'm beginning to get it, but why does it change the way the pencil looks?
Well, in air, light travels at about 186,000 miles a second. But in water, light travels only about 140,000 miles per second. Since light travels slower in water than in air, water has a greater optical density than air.
Not only have you lost me with your big numbers and optical densities, but you didn't answer my question.
Okay, let's put it this way. When light goes through air, it travels at 186,000 miles a second. Once it hits the surface of the water, some light is reflected, but some light travels through, into the water. Once the light is in the water, it slows down a measly 46,000 miles a second, and this change in speed changes the direction of the light ray. This explains the pencil looking distorted and broken. The light in the water is actually being refracted.
I think I get it now. So what you're saying is the light is slowed so much in the water that it actually changes the way we see it?
Exactly. I'm glad you get it now.
I'm glad I learned the answer to one of life's most important questions. Why a pencil, upon being submerged in water, changes direction and thickness.
That's not all there is to refraction, though. That is only refraction of light. Refraction occurs in all types of waves. Refraction even occurs in sound waves.
I can't even begin to imagine how that would work.
It's honestly not as scarily confusing as it sounds. When a sound wave is refracted, the right side of the wave slows down when it hits a new medium, effectively changing the direction of the wave. Think of it like a toy car rolling across from a floor to a carpet. The wheel that hits the carpet first is slowed down first.
That's cool, I guess. I don't really know why refraction is important, though. It slightly changes the direction of sound and tricks us into thinking a pencil is bigger than it really is when it's in water. Why should I care about refraction?
Well, without refraction, we wouldn't be able to see any photographs, watch any movies, or watch any TV shows. Not only because without refraction cameras would not exist, but we would also be effectively blind.
What is that?
Well, our eyes need to refract the light we see to fit the refraction index in our eyes. About 80% of refraction occurs in the cornea, and about 20% happens in our inner crystalline lens.
So why wouldn't cameras work?
Images formed in cameras by refraction work pretty similarly to the way our eyes form images, but the way they focus and accommodate images is done differently.
Well, I guess if refraction is responsible for cameras and us not being blind, I'm glad it exists.
Me too.